Hi, everyone. Um, it's 5:30 Israel time, and welcome back. And in this second hour, we're going to pick up where we last left off. We're going to finish up talking about tensor products of quantum systems and the rules regarding these multi-qubit systems. And then we'll jump into quantum computation. I've been checking out the Slack, and there's lots of really good questions, so keep them coming. All right, so we talked about how we describe the state of, say, 2 qubits. Well, let's talk about the 2 things that can happen to these 2 qubits. The first thing is measurement. So the measurements are pretty straightforward. It's what you might expect. So let's say that you have a general 2 qubit system, and it's this superposition over classical states I comma j with these amplitudes alpha ij. If you measure these 2 qubits in the standard basis, then you're going to get 2 bits out as the outcomes. And the probability of bits I comma j will be alpha ij magnitude squared. And then after you measure, the state psi will collapse into I comma j, the classical state. All right. So that's pretty straightforward, should make sense. Let's talk about partial measurements, which are a little more complicated. So let's say you have a 2 qubit system, but you only wanted to measure the first qubit and you didn't want to do anything to the second qubit. I mean, you might not even have the second qubit in your hand. You can imagine that, for example, in a cryptographic protocol, maybe one party, Alice, has 1 qubit and Bob has the other qubit, and Alice just decides to measure her qubit. What happens to the overall state? So there's some rules regarding that. If you measure the first qubit of a 2 qubit state, maybe let's just draw it, so you can just imagine it. So here's 1 qubit, here's another one. Let's say that their joint state, might even be an entangled state. Maybe it's the EPR pair that we saw a couple minutes ago. When you measure the first qubit, you're going to get a single bit as an outcome. And mathematically, to calculate what are the probabilities of getting this outcome I, is you first have to project your state psi onto all the terms where the first, the first bit of the basis state matches your outcome. So we're just going to get the sum over j of alpha ij ket ij. All right, so you're just basically deleting terms from your sum. So this is going to be an unnormalized state. And to find out the probability of this outcome, you just have to take the norm squared, the length squared of the state psi prime. Okay, technically psi prime I. So that's the probability of the outcome. And then you have to renormalize this state to get a new quantum state. So you just divide by 1 over the square root of this probability. And that is going to be the new state. That's what the state gets updated to. So you'll see, so we get, you can write this way. You can also factor out the first qubit. The first qubit is collapsed into the state I, like you might expect. And then the second qubit, it looks a little different. It's changed into this single qubit state now. So this is state of the second qubit after the measurement. And so one thing to observe is that, even by just by measuring the first qubit, suddenly the whole system changes. And now the state of the system is an unentangled state. Right, so the state originally might have been entangled. Maybe this EPR pair or whatever. But when you measure it, and now factors into a state I, tensor, some other single qubit state on the second qubit. Okay, so let's run through a very quick example. So let's say we have this state psi. This is an entangled state. So let's see what happens when we measure the first qubit. So there's 2 possible outcomes, 0 or 1. So let's say we have outcome 0. the first thing you do is you just delete all the cases when the first qubit is not in the state 0. So we get square root 2/3, 0, 0, plus square root 1/6, 0, 1, right? And then the probability of the outcome will just be the length squared of this vector. Okay, so it's easy to calculate. That's 2/3 plus 1/6, which I believe is 5/6. So with 5/6 probability, measuring the first qubit will yield outcome 0. And then the post-measurement state is just going to be this psi prime 0 divided by the square root of this probability. So it's, you get 6.5 square root times psi prime 0. Okay. And so, you can work out what the amplitudes of the state are, and that's going to be the post-measurement state. Well, actually, let me just write it out so we get 0 tensor, and then what is the single qubit state for the right-hand qubit? Well, it's going to be, see if I can do this arithmetic quickly. So this will be square root 4/5, 0 plus square root 1/5, 1. Okay, that's going to be the state of the second qubit. And you can do a similar calculation for outcome 1. The probability of this outcome is just going to be 1 minus the probability of the other outcome. So this is going to be 1/6, right? And the post-measurement state, this one's easy to calculate. I mean, you can see that in the original state, there was only one term that had the first qubit being in the state 1. So that's going to be the post-measurement state. Okay, both qubits end up in the state 1. Okay, so that's an example, and now you should be able to do any other example on your own. Okay, so that was partial, measurements and partial measurements. Now let's talk about unitary evolution, right? Isolated evolution. And again, we have unitaries acting on this larger tensor product space. How can we describe them? Well, one way of talking about them is to build them up from unitaries on the smaller systems. So let's say that we have a single qubit unitary U acting on one qubit and a single qubit unitary V acting on the second qubit. To describe how both qubits evolve jointly, we just take the tensor product of these unitaries. Okay, this is going to correspond to a 4x4 matrix. That's also unitary, satisfies all the same postulates, axioms of what being a unitary is. And the matrix representation is as follows. If U looks like this and V looks like this, then U tensor V is going to be this following, block matrix multiplication. I should note that this choice of how we represent this matrix representation, it really depends on how you label your rows and columns, right? So for example, when I said that, if we have this tensor product state 0, 1 as corresponding to 0, 1, 0, 0, that's a specific choice because we're saying that this entry, the second entry of the column vector corresponds to 0, 1, right? And so how you represent these tensor products of matrices will depend on that representation. I should note that as we go on, we won't really work with concrete matrix representations of these tensor products because after a while it just gets too large to write. And so this is just to to help you get like a concrete foothold into what these tensor products mean. But really, we will rarely write out the matrices like this. Okay, so a couple quick examples. So let's say that we have a 2-qubit state, starts off in 0 tensor 0, and we decide to apply U tensor V, where both of them are the Hadamard matrix. Right? So remember that this is the Hadamard matrix. So U tensor V applied to psi, well, we can sort of split up the, again, when you're doing these multiplications with the tensor product, you have to match up the slots. So this U has to be applied to this 0 here, and this V gets applied to this 0. So this is the same thing as U applied to 0, tensor, V applied to 0. And we know since U and V are this Hadamard matrix, and if you remember from what we saw before, this is just a plus state tensor the plus state. Right? And we can write this out in terms of the standard basis vectors. This is 1/2, 0, 0, plus 0, 1, plus 1, 0, plus 1, 1. Right? So that that's this particular example. In the second example, it's you can do it a couple different ways. One way is you can just go term by term and apply U tensor V to each of these 4 terms. Right? That would be kind of a long way of computing it. A faster way is to first realize that this state psi can be factored into a tensor product state. So if you look carefully, this is equal to, I believe, the minus state tensor the plus state. Right? You can check that this is true. So then computing this, the action of this unitary on this state psi is now very simple. Right? This is U applied to the minus state, tensor V applied to the plus state. U and V is still this Hadamard matrix, right? And it's this change of basis, and you get 1 tensor 0. So this is much faster than going, applying U tensor V to, these 4 terms separately and then sort of collecting all the terms and so on. And so this is a faster way. Alrighty, and I'll skip this example because it's very much similar. U tensor V is an example of a non-entangling unitary because it's a unitary acting on 1 qubit, tensor unitary acting on a 2nd qubit. But in general, not all 2-qubit unitaries look like that. Most of them, by some definition of most, they're entangling. They create entanglement between 2 qubits. So the most important 2-qubit unitary that you'll have to think about is something called the C0 gate, controlled knot. And it acts on 2 qubits, and it has the following definition. We're going to define it on how it behaves on the standard basis vectors, and this tells you how the unitary acts on all vectors by linearity. So if you have 2 qubits, one that starts in state x is 0 or 1, and the 2nd qubit is 0, then it essentially copies x into the 2nd qubit. Right, so the qubits have different functions. The first qubit is called the control qubit, and the 2nd qubit is called the target qubit. If the target qubit's in the state 1, then it flips the control qubit. Or another way of saying it is that it basically adds the control qubit into the target qubit. Right, so this is x plus 1 mod 2. Okay, sort of a quick example. Let's say we now want to apply C0, the C0 gate to not a classical basis state, but plus tensor 0. So we can open up what plus tensor 0 is. This is C0 applied to 1 over root 2, 0, 0, plus 1, 0. And then you can bring in the C0 by linearity. Okay. C naught leaves the 0, 0 state alone. But when you apply it to the second term, the control qubit is in the state 1, so you have to flip the second qubit. So you get the state 0, 0 plus 1, 1, which is this EPR pair, right? And so you can see originally the state was unentangled. It was plus tensor 0. Now it's this entangled state, the EPR pair. Okay. So that's the C naught gate. And there's an explicit matrix representation of the C naught, which I won't write down because it's actually not that useful. Okay, so that's the C naught gate. This brings me to the no cloning theorem. It looks like the C naught unitary is kind of cool because it copies bits, right? So if you have x tensor 0, where x is a 0 or 1 standard basis state, then it creates x tensor x. So it copies things, right, in a natural way. You might wonder, is it possible to have a unitary that doesn't just copy standard basis states, but copies arbitrary states? And in quantum information and quantum physics, this is not possible. And this is called the no cloning theorem. You cannot copy general quantum states. And so the informal statement is that there's no such thing as a quantum Xerox machine, right? There's no unitary that takes in an arbitrary state psi, right? This state psi doesn't, not necessarily a standard basis state, tensor 0, which we call an ancilla qubit, and creates two copies, psi tensor psi, right? For all possible 1 qubit state psi. There's no such unitary. And this, actually has cryptographic ramifications. I mean, this might be something that gets talked about later in the course. Classical information you can copy all over the time, right? And when for example, in complexity theory or cryptography, you really make use of the fact that you can copy strings all over the place. But in quantum mechanics, in quantum information, it's more complicated. If you have a quantum state that someone hands you, there's no general way of creating another copy of it. Let's see a quick proof of why this is the case. So you say, well, suppose for contradiction there was such a unitary that could copy all single qubit states. Well, it turns out to be a violation of unitarity. So let's say you had, you tried to copy the 0 state. Well, sure, it copies the 0 state, no problem. And let's say you try to copy the plus state. Well, since we're assuming that there is such a unitary, then this would create plus tensor plus. But remember, one of the things we said earlier was that unitaries preserve inner products between states. So the inner product between these two states if you can calculate it, this is 1 over square root 2. But on the other hand, the inner product between these two states is different. This is 1/2, right? So these are not the same numbers. And so therefore, this is a contradiction. So this contradicts U being unitary. Right, so this is the a way to prove the no cloning theorem. All right, so this brings me to the end of this discussion about exponentiality of quantum mechanics. We talked about putting 2 qubits together, but of course, in order for things to be interesting, you want to put many qubits together. And so if you put n qubits together, the Hilbert space is this n-fold tensor product, and it has dimension 2 to the n. Every time you add a new qubit, the dimensionality of the space doubles. And a general n qubit state will be written as a superposition over n-bit strings x with amplitudes alpha sub x. So there's 2 to the n amplitudes just to describe the state of these n qubits. that sort of tells you that the state of these n qubits is this really complicated thing, right? There's exponentially many amplitudes to keep track of. And when you apply an n qubit unitary to this n qubit state psi, by linearity, it's now going to be a superposition of this unitary u applied to all 2 to the n different basis states, right? So at least mathematically, it looks like when you apply unitary, when you apply this transformation to these n particles, you seem to be doing exponentially many computations in parallel. At least it looks that way. And so you might say, well, maybe this is where the power of quantum computation comes from. But it's a little more subtle than that. That sort of tells you that nature seems to be doing an incredible amount of work for us, but all of that extravagant work is hidden behind the veil of measurement. So you can apply this unitary to this n qubit state, but if you actually wanted to extract any information from this computation, you have to do a measurement. And we've seen that measurement is destructive. After you measure, your state gets collapsed. It changes. And so you can only get access to this exponential information in some limited way. And so there's this tension between the exponential nature of describing these states versus their fragility, their fragileness coming from measurement. Okay, so that's it for sort of this first part.